a chance to be here and listen to the speakers, and I have to say I've been completely blown away by the depth and breadth of what's been talked about. I'm actually reminded of a famous San Diegan, Admiral James Stockdale. You may remember this guy. He was Ross Perot's running mate back in the day. And remember that presidential debate where he got up and he said, "Why am I here?" And I kind of feel that way right now in terms of what I could possibly contribute. Now, part of the reason maybe I'm here is we are a sponsor of this event, so you know, that's that. But maybe what I can contribute is from a company standpoint. My company, Life Technologies, does about $3.5 billion a year. Very profitable company, earn almost $1 billion a year. We're based here in San Diego, and a lot of what you have been hearing about and will hear about are things that we center our work on to try to advance. I mean, we fundamentally believe that biology holds the answers to the big challenges of the 21st century. And what I want to share with you is a bit of our roadmap of how we are going to tackle some of these big challenges, really around molecular medicine, cancer, and even beyond that, in dealing with some of the broader societal implications with science. So first, to set up maybe about cancer and molecular medicine, you've heard a lot of it already, but let me try to do it from a bit of a soap opera standpoint. And you know, in terms of a woman named Sarah. Now, there have been remarkable advances in medicine, we all know. But medicine today is still practiced at a very imprecise level, based on averages and populations. And quite frankly, most of the clinical trials have been done on Caucasians. And so here we have a woman named Sarah, a middle-aged woman. She feels her breast, she has a lump, and obviously that's incredibly, incredibly stressful and emotional. So she goes to see her doctor, and her doctor suggests a mammogram. She has the mammogram. It comes back that, yes, it is a tumor. The doctor then says, go get the biopsy. They do the biopsy. Biopsy comes back that it is cancerous, and worse, they caught the lump a little bit too late, and it's metastasized. Now, beyond the lumpectomy, which is invasive and painful, she then has to subject herself to radiation or chemotherapy or both. And I think we know that the drugs involved here, as I just mentioned, are very inexact. In fact, we've done work with a lot of medical centers. The oncologist you choose, really their experiential set determines greatly what therapeutic agent they prescribe, and 1 in 5 of these chemotherapy agents work, so most of them don't work. In the case here of Sarah, as we kind of work through her case study and her story, it doesn't have a very happy ending. They caught the lump too late, and she doesn't survive, as 40,000 women in the United States alone this year will not survive from breast cancer. So this is really a big issue and obviously a big challenge here in our time. Now let me cut forward. I think we know, as we're hearing here, there are some incredible advances being made in science and medicine by scientists and by doctors. We are in the midst of a genomic revolution. And so let's turn the case of Sarah one more time now, but in the modern age, in a precision biology age where we can make a difference. So now Sarah knows her family history, and so she goes in for an early gene test to see if she has the predisposition for breast cancer. In fact, she does. And so her doctor tells her, and I think it's good advice, that you should get mammograms done earlier than you would normally do at her age, and do them often. And because of that, when that lump finally does appear, they catch it far earlier in the onset. They're able to do a very minimally invasive procedure to remove it. But more importantly now, in the world of genetics, they then sequence that tumor. That is, they read the entire DNA of that tumor, and in that future world, they're able to prescribe the exact combination therapy that works for her biology, and she's able to have a normal life while it's fighting the cancer, and this is now a story of survival. And that really is what we're trying to do here over the next decade, is create that story of Sarah, the before, and really more importantly, the after. Now, before I get into DNA sequencing and gene tests, and really the theme of this particular panel section, let me just kind of make sure we're all grounded on cancer, what we think about in terms of cancer. So here we're going to go deep into the breast tissue. We're going to tunnel in and look at inside the cells, ultimately getting inside the DNA. Cancer is one thing. It is a disease of DNA, of damaged DNA. Now, the human system is incredibly robust. redundant systems and the like, and able to bypass things. And so in the case of cancer, it's usually not one variant of your DNA, one mutation. It's multiple mutations that ultimately cause the onset of cancer. And so what we're trying to do here then is read the DNA from beginning to end and find those few mutations that happen that ultimately stimulate the onset of cancer. And so that's the technology of DNA sequencing that I'm going to share with you about in a few minutes. Now, just in terms of DNA sequencing, it's really a remarkable story of what's taken place. Just if we could go back 10 years to the year 2000, Craig Venter, who was on the stage last night, and Francis Collins, who's now the head of the National Institute of Health, stood at the White House where they celebrated the completion of the first genome. This was a federally funded project, about $3 billion, and they did one genome just 10 years ago. And we'll come back to that to show you how far and how fast this technology is moving. But before we get into sequencing, I think if we could just jump to the next one, it's important to explain DNA and how you read it. So, DNA is what we're all comprised of. It's 4 basic chemical substances represented by A, T, C, G. And the way I would kind of give you a more physical analogy of what's going on inside those trillions of cells that you have in your body is that it's like an encyclopedia. And so you have 3 billion base pairs in your DNA, and they could all be categorized into volumes of an encyclopedia. Those volumes have chapters, and each page of a chapter has a letter on it, one of those letters. And so when we read the DNA completely from start to finish, we read the encyclopedia from the very first page to the very last page. And we read it in order, and what we're looking for in cancer is a mistake of one of those letters on page 5, another mistake on page 50, and one more mistake out on page 1,000. That's the mutations we're looking for that cause cancer, and that's the needle in the haystack that you're trying to do with the technology. And you can't make mistakes because we're dealing with life and death here. But if we can catch them and we can read them properly and we read them often and compare it to where you are and where you've been, we can really then start to catch cancer much, much sooner. Now let's talk about the current technology of what's going on here in sequencing. This here is the solid system. It's from my company. This is a field that is moving at a breathtaking pace. So I said 10 years ago it was about $3 billion to complete the first human genome. Today, most researchers in very advanced medical centers, advanced universities can use a machine like this, and they can decode a genome in about 14 days and for about $20,000. Now, I won't make you do the math, but this has moved at far faster pace than the venerable Moore's law that we know about in the semiconductor industry, and it is not slowing down. In fact, what I want to share with you here is that we just had my genome done. I won't share with you the results because at least my wife will want to understand finally what it is about me, but we were able to use this machine to decode my genome for under $10,000 and doing it now in 10 days. But what's more exciting, I think, is really what's going to happen in the next 3 to 5 years. And I'm going to share with you the vision of what's going on in our labs right now, of how we take this technology and move it out, democratize it, move it out into other hospitals, other ultimately physician's office, oncologist's office, where they can sit down with you, they can read your genome in about $1,000, and they can do it in about 1 day. And they can do it incredibly accurately. This is the technology that's underway, and again, it's coming. And it's moving far faster than Moore's law. The more interesting thing, perhaps, is not so much the technology, it's that the medical profession has to keep up, and it really hasn't. A whole new breed of doctors has to be considered, perhaps. Maybe molecular doctors. I don't know the term. But people who can ultimately read these genome scans, interpret what's going on, and then make and give advice. Look, it's very similar to the rise of the radiology specialty. We used to only have X-rays, then we had CT scans and MRIs, and these images got ever more complex and sophisticated. The same parallel path has to now take place in terms of genetic scanning and ultimately diagnosis. Now, let me take you inside this machine, because I think there's one just interesting, cool technology that I'll share with you, something called a quantum dot. This is one of these nanoparticles that you read about. We spent over $100 million developing the quantum dot. And the quantum dot, for those of you who are into photography, you know that great pictures are all driven by the lighting. And actually in DNA sequencing, that turns out to be one of the essential key technologies is the lighting. The ability to shine a spotlight on your DNA and then read it instantaneously at an incredibly breathtaking speed accurately. And so this quantum dot is just one of the key technologies that will be that flash bulb inside the reading of the DNA that will allow this $1,000 genome to happen. And that's going on in our labs as we speak. So now let me just cut forward and talk about this technology, as I said, is moving beyond. It's democratizing. We saw it originally start in the great medical centers like Harvard and Stanford, and now it's moving out. It's moving out to other universities. It's moving out to other hospitals, and it's moving all across the world. This is not just onesie or twosie. These are hundreds of systems being sold now in 2009 and scaling up at over 50% a year. So the technology is starting to be used, understood, and applied into this world of molecular genetics, into the treatment of really starting off mostly in cancer. Now, I've spent a lot of time talking about DNA. Let me cut forward in another area of our company that we spend time on in thinking about molecular medicine, and that's in regenerative medicine. You heard last night about some incredible work done at Wake Forest. We would certainly claim no credit, but a lot of the underlying tools for that bladder regeneration were from Life Technologies, the media to grow the cells and things of that nature. The great thing here about stem cell research is just how quickly it has moved from being a controversial subject using embryonic stem cells to where now we're able to de-differentiate using your own skin cells, reverse the course of time, turn them back into your original stem cells, and the hope is ultimately using those into the therapeutic use. In fact, if we just cut forward, let's just pretend for a moment that this is a diseased pancreas. It's a pancreas that had cancer, a portion of it had been resected, and this gives you an image of how that regeneration will ultimately take place. We'll take your skin cells, we'll reverse them, turn them back into your original stem cells, we'll implant them onto the surface of this pancreas in vivo, and then through the wonders of science, they'll regenerate and grow, ultimately to replace that part of the pancreas that had been removed. Now, there's a lot of technology involved here. What we focus on is how to grow those cells properly, how to make sure that they're in the pancreas and haven't migrated to other parts of the body. So there's key visualization techniques that have to happen. But, this is coming, and it's not rocket, I should say, it is rocket science, but it's not science fiction. And we think it's going to revolutionize, really, the field of medicine just as much as DNA sequencing will. Now, if we move beyond medicine, really where I wanted to also spend a few moments, if you think about it, if we can read DNA from the very first letter to the very last letter, the next step of that is we can probably recreate the DNA as well. Or we could actually make the entire DNA from scratch. It involves some very advanced chemical synthesis. It's a little bit of Jurassic Park, but it's being worked on, and we're aggressively working on it. Because if you could actually then create entirely new strands of DNA, you can ultimately then, as Craig Venter shared with you last night, design microbes to do good for society. They would sit in these large bioreactors. They could make fertilizer for crops. They could make medicines. They ultimately could make new fuels that are very environmentally friendly. And it's a future that's happening as we speak also at a similar breathtaking pace. And the interesting thing, it's all the same technology. Now, obviously, it's differentiated here and there, but basic technology to power both the molecular medicine revolution we're talking about and the synthetic biology revolution that has to take place. So just to wrap it up, one of the reasons I'm here is, we fundamentally believe in this future. We believe it with not only our work inside the company, but through our foundation. And one of the things we've done is work with Craig and his team to sponsor that Sorcerer II expedition to go out and find those microbes, understand what they are, really find the incredible genes that may exist in them, and power this synthetic biology future. The other reason, though, that I want to be here is to just talk about what we have to do really as leaders in medicine and science and business. Because one of my greatest fears is that we won't achieve the full potential of the power of life sciences. Now, the life sciences, in my view, is what the 21st century is all about. we could radically change our country. We could change the standard of living. These are great jobs, high-paying jobs, high intellectual jobs. And this could be the power of the new economy going forward for our country. But I worry that if the leaders really don't come together and think about all the different implications well beyond the technology, because technology actually will probably be the least of our issues. But thinking about the economic implications, the privacy implications, how we contain certain things if we're doing synthetic biology, all of this stuff, all of these issues have to be worked out. And they got to be worked out kind of out in the open in a give and take way, in a very unfearful way. And so it's really my hope that this group, this TEDMED conference, can stimulate that type of dialogue over the next couple of years, because at least what I've been able to share with you, the future is incredibly bright, and we're just trying to do our own little part to make it all happen. Thanks very much.
I wanted to say that was